All right, so now we want to talk about the origin of the elements in the periodic table of elements. So if you look at the periodic table, you'll notice that there is a lot of different elements. So you got the oxygen that you're breathing. You have water, which is composed of oxygen and hydrogen. You've got the chair that you're sitting on, which is made of plastics, which has a lot of carbon in it. So where did all of these elements in the periodic table, where did they originally come from? So the current theory is that most of the hydrogen and the helium came from the Big Bang. So we think that the entire universe began between 12 and 14 billion years ago as a small, dense, hot kernel of energy and mass that was about the size of a proton. Actually, even smaller than a proton, because inside of protons are quarks. So we think that the entire universe was crammed into something that was even smaller than a quark. It was incredibly dense, and it was also had an incredibly high temperature. And then for some reason, space and time began to expand, and so the universe began to get larger and larger. Well, the temperatures were so high that at first the universe consisted of matter and antimatter. Then, as it cooled off, it then started to coalesce into protons and neutrons, which were very, very hot. Okay, but then eventually it cooled to the point at which those protons and neutrons started to collide with each other, and you had the first nuclear fusion in the history of the universe. And so originally, the universe consisted of basically protons and neutrons, so there was a lot of hydrogen, and then through nuclear fusion, it made a lot of helium. So that today, the universe consists of approximately 75% hydrogen and about 24% helium, with about 1% all of the other elements in the periodic table of elements. So this is going to explain where did the hydrogen and the helium come from. So then, as the universe continued to expand, it continued to cool off, and eventually it got to the point at which gravity started to grab onto the hydrogen and helium and started to compress it again. And so as these balls of hydrogen and helium started to collapse, their temperature and pressure started to go back up again until they reached a critical temperature and pressure at which thermonuclear fusion began to occur, and hydrogen began to be converted into helium again, and you have the birth of the first stars. So the first stars are going to be converting hydrogen into helium, and that's what a star does when it is living. But over millions of years, what happens is the star begins to use up its hydrogen. And so at some point, there won't be any hydrogen to convert into helium, and then that star is going to begin to die. Now, gravity's always there. So the reason why a star is a certain size is because the nuclear explosions are trying to make the star bigger, but gravity is trying to make the star smaller. And as long as those two forces are in equilibrium, the star remains at the same temperature, the same size, the same pressure. But as soon as a star begins to run out of hydrogen, then the nuclear explosions begin to die down, and gravity's always there, so gravity starts to pull the star in. And as it gets smaller, it starts to heat up. The pressure goes up, the temperature goes up, and in some stars, the temperature will go up so much that heliums are going to start to smash together, nuclear fusion again, And then this is going to start to produce the element carbon in the periodic table of elements. So this explains where hydrogen, helium, and carbon come from. And then there are also little side reactions as well that can produce the elements between helium and carbon. So that's going to keep this star alive for a little bit longer. But eventually this star is going to start to run out of helium. And so gravity's always there. It's trying to pull it in. And so some stars are going to get hotter still, hot enough that the carbon can then start to be converted into the next element, which is going to turn out to be oxygen. So let me rephrase this. So it's going to turn into oxygen here. And then in even hotter stars, oxygen then can be fused into neon. And then finally, neon can be eventually fused. And so there would be some other reactions here. So I'll just put ... And then eventually it could be fused into iron. Now only the very, very biggest stars will be able to manufacture iron in their cores. But this is really bad because do you remember when we talked about iron, we said that if you take iron and you smash it, that would be nuclear fusion. It does not produce any energy. And if you take iron and you pull it apart, so that's going to be nuclear fission, it doesn't produce any energy. So that means that the nuclear explosions are going to die down. And gravity's always there, so gravity is going to pull this thing in, and then it's going to explode. And we're going to call that a supernova. So we've generated all the elements up to iron through nuclear fusion processes in a star that is living and then dying. So the elements larger than iron are going to be formed during these supernova events. So this star, when it explodes, gives off so much energy that it can fuse even heavier elements. So it could fuse, for example, so I'll put ... uranium. So uranium, normally, when you fuse uranium, it's not going to give off any energy. So uranium gives off energy when it fissions, when you break uranium apart. But the supernova event gave off so much energy, it was able to actually fuse uranium and those heavier elements in the periodic table. So everything that you see around you today is either a result of the Big Bang or stars during their normal process of living, or when a star explodes. So I've got a little video here, the origin of the elements on YouTube, that goes through these processes for you. All right, so that finishes up this lesson on nuclear physics. So let's take a quiz over what you know in just a moment.